Hi, good morning, everybody. My name is Timain, and today I'd like to share with you a little lecture on challenges of helicopter design and operation. I'm going to go through the modules. I just wanted to let you know that short definitions are going to be available to you on the discussion section of your My Canvas. So this is about challenges of helicopter design and operation, a not so simple guide. Throughout this course, you're going to be learning concepts, a few concepts that some of which you might already be familiar with, and others that are going to be brand new to you. So my name is Timain. Good morning, and welcome to Challenges of Helicopter Design and Operation. This is a not so simple guide to some of the challenges that we're faced with in the design and operation of helicopters. This is important to us as aircraft maintenance engineers or as pilots because these challenges explain why some of the difficulties and why the complexities of the helicopter or rotary wing aircraft are the way they are. So first of all, my name is Timain, and it's pronounced Timain. My last name is Ojaye, and it's been a pleasure to meet all of you today. And here are a few of our learning objectives. We want to recall what helicopters are, understand what fundamental operating principles govern flight of rotary wing aircraft. We want to be able to analyze some basic challenges and discuss some possible ways that we've been able to walk around those challenges. So these are examples of some of the rotary wing aircraft that we're going to be looking at. This is a Chinook, and we have the Ospreys. We have several different designs. This wouldn't be a complete, so having looked at that now, I want to get your pre-course assessment on your thoughts about some of the possible challenges. There's no right or wrong answer here. I'm just going to go ahead and join the Kahoot as Tim Bob. Okay, so let's go ahead and start this Kahoot. Yours. The task is to reorganize these problems from top to bottom in order of increasing importance, most challenging on top. So what do we think the most challenging is? I would go with helicopters are too unstable. Then I would go with probably the fact that they don't have enough range. Then perhaps I'll go with the fact that they're too slow. Maybe noisy first and then too slow. Yes, that will be my final answer. And yes, so there is no right or wrong answer here. It's really just about how you choose to perceive these. So I'm going to pick up from LO1, Learning Objective 1. And this is just to recall what lift is and what similarities we have between fixed wing aircraft and rotary wing aircraft. So on the fixed wing aircraft, we know that what separates any of these craft from your vehicle, your automobile, is the ability to create and sustain lift. So some of the factors for lift production include the wing area, which there's nothing that we can do about it in a helicopter. In a fixed wing airplane, we could extend the flaps to increase that wing area. In a helicopter, there is nothing we can do to extend the wing area. With regards to air density, there's also very little that we can do to affect that, even though it plays a considerable role. But one of the most important factors are speed. And if you look at speed here, its importance is squared. So that means that we get an exponential increase or decrease of lift with increase in speed. We also have the angle of attack. And these two factors are the ones I'd like you to put at the back of your mind: angle of attack and speed. So for helicopters, we know that they're under the category of rotary wing aircraft, and that they're VTOL, vertical takeoff and landing. They're used for many different applications. Some of the fundamental principles of flight for a helicopter is the fact that it uses a rotating airfoil. So we have a wing, hypothetically, of a fixed wing airplane, but instead of being fixed and moving through the air or air rushing over it in a wind tunnel, we have a rotation. And that's the primary principle, is that lift is generated by rotating airfoils, which are the rotor blades. The next important thing is about that angle of attack that I asked you to think about there. So for fixed wing airplane and rotary wing, the definition for angle of attack remains the same. It's basically the angle between the chord line and the relative wind. However, in a helicopter, the relative wind has two components, one of which is the translational, which is similar to a fixed wing airplane. The airplane is moving through the air, so it's going to generate some relative wind from that. But we also have a combined, we also have a rotational relative wind. So because it's rotating, being driven by a mast, this rotation actually combines with the other relative wind to give you your combined relative wind. The next operating principle is lift, weight, thrust, and drag. In a helicopter, in a hover, that means that the airplane is not moving forward, back, left, or right. It's just hovering. This is quite simple for the helicopters to do. The helicopters do this very effectively. In fact, it's quite easy. You raise the collective, and this would change the pitch of all the blades simultaneously. Quite easy fit to figure out. However, and the only type of drag that is produced here is induced drag, because induced drag, as we learned before, is drag that is produced as a result of lift production. The next is thrust vectoring. Thrust vectoring, this is where things start to get tricky or complicated for helicopters. Because we have a combined lift and thrust, when we have to move in any direction, we're going to start producing form drag, which is not unusual. The complicated part is the fact that we have a lift and thrust that's now divided. Since we don't have primary thrust producing engines like you would on a fixed wing aircraft that take advantage of Newton's third law: for every action, there will be equal and opposite reactions. So the jet blast going backwards, the helicopter or engine moving forward. We don't have that variation, except, of course, in the Eurocopter. What we have is to split our lift into two components. One, the vertical component of lift, the other, the thrust. So every time we try to move forward, we're going to lose some lift. And this can affect at the altitude that is being maintained. That's one of the primary challenges. The next would be to, the next would be to analyze lift dissymmetry. So this is a scenario or a phenomenon whereby the advancing half of the rotor discs is going to produce more lift than the retreating half. What does this mean? This essentially refers to, so I like to think about this as the minute hand of a clock. So imagine that a helicopter had only one blade. This is very uncommon, but imagine that it had only one blade. So that blade would go through a half where it's the advancing half of the rotor disc, and the other would be the retreating half, depending on the helicopter's direction of motion. An example I like to use here is if you were to go to the airport and you're rushing, and on your left you had an escalator that a travelator that was going forward, and on your left and on your right you had a travelator that was coming towards you. If you chose option A, you would be going this way, you were running. Your speed would be the combined speed that you were running before you got on that travelator, plus the speed of that horizontal escalator. So that would be similar to your advancing blade. You're going to produce more, you have more velocity, and like we mentioned, more velocity will equal exponential increase in lift. On the retreating side would be that travelator that's coming towards you. If you were to run onto that, you would definitely be slower. It would have been better for you to go in the middle and just go by foot as opposed to getting on this travelator that's coming opposite to you. So if this is the direction of flight, the relative wind is coming. The translational relative wind is what's coming at you. The rotational relative wind, however, is going to be multiplied because we're traveling in this direction and the blade is moving as well forward between the 6 o'clock, 3 o'clock, and 12 o'clock position. This and other methods are, this helicopter image on the right here is known as a coaxial blade system, in which the two blades rotate in opposite directions. So in order to even out the amount of lift produced, we have two blades that are rotating, two rotors that are rotating counterclockwise. So one of them is rotating in a clockwise direction while the other one is rotating in a counterclockwise direction. This helps us cancel out that dissymmetry of lift, because otherwise we would have a tendency for the helicopter to roll in the direction of less lift. This now brings us to blade flapping. So blade flapping is a method that is used in both a rigid rotor system, semi-rigid, and fully articulated rotor system. The advancing blade, because it's creating more lift, flaps its blade up, and at the same time using a delta hinge is able to rotate that inward and reduce the blade pitch. That blade pitch is what will affect the angle of attack of the blade and hence reduce the amount of lift produced on the advancing half of the rotor disc. In contrast, the retreating blade that's moving away from the direction of flight will increase its blade pitch as well to compensate for that, and that process is known as blade flapping. So the blades move up and down relative to this flapping hinge. The idea of a retreating blade stall, however, is that advancing blade is moving faster, the retreating blade is moving slower. As we try to break that forward speed limit and try to go faster and faster, the difference becomes more and more, and that retreating blade has to seek a much higher and higher and higher blade pitch until it eventually stalls. So the combination of a slower blade moving at a very high pitch exceeds that critical angle of attack, and then we have a stall. So these are a few helicopters that we know of, and their speeds. These are one of the fastest ones, and even these only move at 300 kilometers per hour. We know that the speed of sound is about 1,225 kilometers per hour, and we know many, many fixed-wing aircraft that can do Mach 1, Mach 2, Mach 3, etc. These are on the fast ends of the helicopters. The Eurocopter is one that features a primary thrust system and is able to produce significantly more thrust and more forward speed because it doesn't rely on tilting that main rotor hub. So in the discuss, I'm going to encourage you to look at things like blade lead lag hinges and what Coriolis effect is before we have our next class. Consider discussing some issues with blade flapping and talk about the fenestron tail, talk about blade pre-coning or the reason why we have an inverted H-stab. Think about a stabilizer bar and the gyroscopic effect. So in summary, we know that helicopters are engine-powered rotary wing aircraft. The fundamental operating principles include rotating airfoils. Some of the challenges that we have is that they have limited speed, limited range, and instability. Discuss current solutions, do your homework. So if you go into your My Canvas, this is what you should see. You see modules under this course, and you'll be able to look in the announcement section to get short definitions or new concepts that I've posted there. We also show some short videos or 3D animations to help you understand the symmetry of lift. We have in the lecture section, we have the lecture slides that includes more wordings, more on what we've just talked about. We also have a test 3 practice quiz that you can use to prepare yourself for the quiz. There's a group discussion forum that has been created for you. If you go into discussions here and you're able to post your comments on some of those topics we just mentioned and comment on at least one of your classmates' posts.